Good day, everyone. Today we'll be doing our session 2 for the day. So, our session of the day will be numeric data types. So, before we continue, I just want to get into our objectives of the session. Firstly, we've got distinguishing between different numeric data types, and we've got identify different logical data types and distinguish between different internal representation of data types. And lastly, we've got identify different logical operators. So what I've done, I've just done I've got some slides that I've made information based on our session of the day. So before we could continue on our learner guide, I just want to go through to our slides today for our session 2. So the question would be, really, what is data representation in computer system? Well, data representation refers to the form in which data is stored, processed, and transmitted. So, in this session, we talk about the different uh, the different the different the different numeric data types. So we need to bear in mind that the data is in a nutshell. What is it? It refers in which how data is stored, processed, and transmitted. And we've got 5 different numeric data types. So our 5 numeric data types, it's the first one. It's decimal, which has a base 10, which represents any number using 10 digits, counting start from 0 up until to 9. And we've got the binary, which has a base 2, which represents any number using a 2 digits only, 2 digits, which is zeros and 1. And we've got an octal, which is a base 8, which represents any number using 8 digits, counting start from 0 up until to 7. And lastly, we've got a hexadecimal, which has a base 16, which represent any number using a 10 digits and 6 characters combined, which counting start it comes from 0 up until to 9 and A up until to F. So now going to our learner guide as to going into depth as to what is binary. What we talk about when say binary. Binary notation makes exactly the same way as the decimal notation, but instead of 10 symbols, only 2 symbols are used, which are zeros and 1. Whereas decimal is a base 10 positional notation. Binary is a base 2 positional notation. A digit in binary is usually referred to as a bit. With 1 bit, we have 2 possible values, 0 and 1. I've done some examples on these binary. Just I wanna go through them quickly just to give you a background of what are they talking about. So, for instance, as we have mentioned in that it's the decimal, it's the decimal notation, decimal deci decimal 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 notation. So in decimal notation, we've got our base 10. Counting start is from 0 up until to 9. If you may count starting from 0, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which has a base 10. So let's look at 437. We just want to break down 437 as to what it's all about. Let's break down 437. So we can break down 437 as to 400 plus 30 plus 7, which will give you 437. And 400, we can break 400 in terms of saying 4 times 100, which is 4 times 100, it will give you 400, plus 3 times 10, it will give you 30, and then plus 7 times 1, it will give you 7. We could further break down the 4 times 10 as to 4 times 10 to the power 2, it will give you 4 times 100, plus 3 times 10 to the power 1. Any number to raise to the power 1, it will give you that number. So 3 times 10 to the power 1 will give you 10, 10 times 2 will give you 30, and then plus 7 times 10 to the power 0, it will give you 1, which will be 7 times 1. So the 10 is the base. So here 10 is our base. 10 is our base. 10 is our base. So now since now we've got in decimal notation, we've got our number counting from 0 to 9, and then in binary notation, we've got zeros and ones. So we know from 0 we've got 0, it's 0, and then from 1 we've got 1, from 1 we've got 1, from 1 we've got 1, and then 1 0 represent number 2, and then 1 1 represent number 3, and then 1 1 and 1 0 0 represent number 4, and then 1 0 1 represent number 5, 1 1 0 represent number 6, and then 1 1 1 1 0 represent number 7, and then 1 3 3 represent number 8. We'll continue further as we go through our learner guide. Just to explain further, let's go back to our learner guide. So in binary 1 bit, we can count from 0 to 1. To count higher requires more bits. As I have explained here, to count higher, it will require more bits. As we could see from our slide, counting further, if you want to count further, it will require more bits. So here we've got 3 bits which represent number 4, which represent number 4. So having 3 bits will represent number 4, and having 4 bits represent number 8. Represent for having 4 bits represent having 4 bits represent, let me just do this just to make it easier for you to understand. 4 bits, yes, 4 bits, 4 bits, yes, having 4 bits, it represents number 8. So this bits 1 2 3 4, it's 4 bits. Let's go back to our learner guide. So in binary with 1 bit, we can count from 0 to 1. To count higher requires more bits. With 2 bits, we can count as high as 3, as seen on the table. In decimal, we've got 0 1 2 3. With binary, we've got 0 0 0 1 1 0 and 1 1. The same pattern applies here as it did in the decimal notation. When a digit in 1 position rolls over from the highest numeral 1 to the lowest 0, the digit to the left increases. To avoid any confusion, it should be explicitly stated here that in binary notation, 10 represents the number 2. It does not represent the number 10. For years, our minds have associated the combination of symbols 10 with the concept 10. This association is strong that it can be difficult to temporarily put aside. It may help to realize the symbols 0 and 1 are merely a convention. If we like, we could adopt any other two symbols such as T and H. Let's say T represents 0 and H represents 1. As we could see here from the table below, we've got 0, 1, 2, and 3. T, as we have said, it represents 0. We've got TT, which states 0. TH states 1. H represents 1. And we've got HT, it's 1, 0. And we've got 1, 1. Unfortunately, we want to express data in a binary notation that our compiler or interpreter will understand. We must return to the conventional symbols 0 and 1. In general, with n bits, we can represent the values 0 to 2 to the power n minus 1. This is the formula, guys. 2 to the power n minus 1 is the formula used within the binary notation. The total number of unique values we can represent when we have n bits including 0 is 2 to the power n. To convert from the binary notation to the decimal notation, we can use the same arithmetic that we used to determine the value of a number in decimal notation. In binary, the value of a bit is multiplied by 2 to the position, which is the power, 2 to the power position, which is n, and again the rightmost position is position 0. So the decimal notation equivalent of the binary 1001 is 1 times 2 to the power 0, which is 1, and 0, which is 0 times 2 to the power 1. 0 times 2 will give you 0, and then 1 times 2 to the power 2, which will give you 4, and 1 times 2 to the power 3 will give you 8. So when you add this in total, it will give you 13. So you should notice that the value of each bit is either a 0 or an integral part of 2. This is true because each bit may hold only one of two states, 0, which in some instances they say 0 and 1 represent true or false in a Boolean expression. So given an 8-bit binary number, the resulting value will be the sum of one or more of the decimal values. So we've got 1, 2, 4, 8, 16, 32, 64, and 128. So I just want to explain how do they manage to arrive here. So I've made a slide as to how they manage to find themselves having the 1s and 2s and 3s, etc., up until to 128. So guys, in our first column we've got the binary notation, and in the last column highlighted in green we've got our decimal notation. So for them, so starting count will start from our right going to our left. So in binary terms, when we count from right to left, our starting point is 0. So we know this is we know that this is 0, 1, this is 0, 1, 2, 3, 4, 5, 6, 7, and 8 bits. So now in 2, using our formula for binary notation, so 2 to the power 0, since this position is 0, it will give us 1. So we've got in position 2 to the power 1, which it has 1 bit, it will give us 2, because 2 to the power 1, anything raised to the power 1, it gives you 2. So we've got in our third row, we've got 2 to the power 2, which gives us 4. We've got 2 to the power 3, which will give us 8, and we've got 2 to the power 4, it will give us 16, and 2 to the power 5, it will give us 32. 2 to the power 6, it will give us 64. 2 to the power 7, it will give us 128, and 2 to the power 8 will give us 256. So this is the binary notation representation of these numbers, so from right to left. So now going back to our learner guide, They say given a 4-bit value, that the list is reduced to, no, no, sorry, pardon me, given an 8-bit binary number, the resulting value would be the sum of one or more of the decimal values. It goes up until 256 in 8-bit. So now, given a 4-bit value, that list is reduced to 1 up to 8. Here's an example. We've done that example, so we won't go through that. So the decimal equivalent of the binary number 1001 is 9. So the key concept is that these are equivalent representation. They both signify the same number. So why use the binary notation? Because it's used to closely represent the way information in physical implemented by a computer. Since an individual bit can only be in one of two states, designing machinery or circuitry to manipulate bits is well understood, and these designs can be aggregated to perform operations on collections of bits. In fact, while a computer's memory can be visualized as a very long sequence of individual bits, most microprocessors are not designed to perform operations on one bit at a time. Instead, the processor's architecture defines the least number of contiguous bits which it may be addressed and manipulated during one machine instruction. This least number of bits that a processor may manipulate at one time is called a byte. In the past, the size of a byte varied from one design to another, but over time, most designs have settled on a byte size of 8 bits. Remember, 8 bits consist of 120, no, 8 bits consist of 256. This is the byte used by processors that implement the Intel x86 architecture, which is the architecture on which most modern PC processors are based. The original version of the x86 architecture provided means to work with a single byte and with a pair of bytes called a word. A word being being composed of 2 bytes is a 16-bit wide field. With extensions to the architecture, the ability to work directly upon 32-bit double words D word was added, and on some machines 64-bit quadruple words Q word may be handled by a single instruction. This gives us the following common primitive data types. A byte is 8 bits, a word it's 16 bits, a D word is 32 bits, and a Q word is 64 bits. Uh, at the source code level, binary notation is readily used to represent numeric data. Decimal notation is much more intuitive, and almost all programming languages support decimal notation directly in source code. Binary notation is usually only used to explicitly indicate the specific bits in a data field. The interpretation of such data is, of course, dependent on the program, but common usages include option flags, data marks, bit patterns, packed data, etc. When binary notation is used, the value of all bits in data field are usually explicitly indicated, including leading zeros. So to specify the contents of a single byte in binary, all 8 bits would be included in the notation. For example, to indicate that only bit 0 and bit 4 should be on, it might be written like this: 0001, 0001. The exact syntax required to specify binary notation depends on the programming language used. So I just want to go through this again. Uh, so to specify the contents of a byte, which is in binary, all 8 bits would be included in the notation. For example, to indicate that a bit only bit 0 and bit 4 should be on, it should be written like this. So we know in which position 1 and 0 would be on. So let's write this down so that we could understand. If we want only bit 0 and bit 4 should be on. On it's 1. So we want in which which position it would be on. So from right to left, counting from right to left. So now we've got 0. So we know that in position 0 this would be on, and then it's going to be 0, it's going to be 1 0 0 0. Let's do this. Yes, let's do this. So it will be 1. Let's change the color. Yes, it's going to be 1 0 0 0 1 0 0 0 1 0 0 0 1 1 0 0 0. So now we need to find in which position. So we will highlight this. So we highlight this to color green. Come on. So in which position? So this would be 1. So here we have our 2. We know this would be our 4. 4 to the power 2 to the power 2 to give you 4. And then this will be our 8. This will be our 16. This will be our 32. This will be our 64. And this will be our 128. So for now we'll leave 256 for now, because we've got only 8 bits. No, we don't have only 9, we've got only 8 bits. So let's focus on the 8 bits that we have. So now our position, they said in position 4, they said in position they want to indicate only position 0 and in position 4 it should be on. So position 0 and 1 2 3 4. So now position 0, it's on. Let's use a different color. Let's go with yes, it's on, and position 4. So from here 1 2 3 4. Am I right? 1 2 3 4 5. It's position 5 for me. Starting from 1, counting down will be 4. 1 2 3 4. So in position 16 and position 0, which is position 4. Yes, position 4. The outcome of this having our decimal will give us 16, and here it will give us 1. So now let's go back to our learner guide. The exact syntax required to specify the binary notation depends on the programming language used. NCC, in fact, does not specify any method for giving literal constants in binary notation. I hope, guys, you have a brief understanding in terms of binary. It's quite complicated. You need to grasp as much as you can. If you don't understand, you are free to contact me on the platform that are being given. So you can contact me, I will explain further, and give you examples. We can do this even together. You can it's 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 you are free to contact me. So let's move on to another numeric notation, which is the hexadecimal. 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 Proceed. Okay, guys. Our next slide is our it's hexadecimal. So using binary notation can be cumbersome and prone to typing mistakes. If we wanted to specify a 16-bit value with all bits off except bit 9 in binary notation, it will look something like this. In free basic syntax, free basic, bear in mind it's a programming language. So in free basic syntax, it will look like this. If you can verify that the 1 is in the 9th position in less than 10 seconds, you deserve a pat on the back. So like what we have done previously on our slide, we having to check on which position on bit 9 is it on. So it's cumbersome for us having to give you, let's say we are given a 32-bit, it'll actually take longer to find out which position bits are on and so forth. So if you could verify, okay, that the decimal notation provides a more compact form, but it retains a visual similarity to the underlying machine representing of a value. Hexadecimal is a base 16 positional notation. It uses 16 symbols. So the hexadecimal digit, we've got 0, 1, 2 up until to 9, and we've got A up until to F. In binary equivalent, it's our 0, we know it's 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, and so forth and so forth. In our decimal equivalent, we've got 0 up until 15. So hexadecimal notation is often abbreviated to hex. Strictly speaking, hex notation would refer to a radix 6 system, but the use of such a system is so rare that you can safely assume that hex stands for hexadecimal. With one hexadecimal digit, we can represent the values 0 to F in a decimal 0 to 15 binary 000 to 1111. Again, this is a positional notation, so the value of a hexadecimal digit is 16 to the power position. So OB12 in decimal notation would be 0 to 3 digit 2 1 B 0. So position 2, we know it's 2, and digit 2 1 digit this. Bear in mind, it's OB. We counting from 3, from 3 going up, from 3 going from 3 position 3 going up. So it's OB12. So we know the reason why I just wanted to clarify this is this number 16. So how did they manage to find 16 is because it's in position 4. Count from our number here, 0, our hexadecimal here, we've got a 0B12. So from that, having in this position, we counting from 3 to 1. So now through our position 0, we've got 2 to the power 4, which it gives us 16. So 2 to the power 6 is 16 to the power 0. It will give us a 2. So now we've got 16 to the power 1, which is 60. And our b, it's 16 to the power 2. It will give us this number. When you will verify 2816, you can verify that with the calculator. And you've got 32 and 16 to the power 3, which is 0. And when you add all that, it will give us 2833. In practice, converting the hexadecimal notation to decimal notation by hand is rare. The utility of hexadecimal notation consists in the compact manner that it can express an equivalent value in binary notation. Since 16 is the fourth power of 2, every hexadecimal digit corresponds to a most 4 bits. In other words, since 4 bits can only represent the values 0 to 15, exactly one hexadecimal digit is sufficient to represent a 4-bit binary value. An 8-bit byte requires no more than 2 hexadecimal digits. A 16-bit word requires no more than 4 hexadecimal digits. This pattern holds for any bit length that is a multiple of 4. Since 4 bits is half the bit length of a byte, 4 bits is called a nibble. So we can say that one hexadecimal digit represents one nibble. Converting a 4-bit binary value to decimal is a relatively simple activity. With a little practice, it can often be done mentally. This makes converting binary to hexadecimal trivial. Here is a 32-bit value generated by flipping a coin with consecutive bits shown in groups of 4 with a illustration of a conversion to hexadecimal. When performed often, this becomes second nature, and intermediate decimal notation can easily be skipped. So we've got HH, which we remember on our previous slide, and it represents 1 and 0. So it's 1 1. So HHTT, so it's 1100, and so forth and so forth. Coin tosses and binary. So decimal equivalent of each, when you add that, it will give you a 12. And in hexadecimal, that's CD, CD6, E, CD, CTC, CTC, CTC. So to convert this value to decimal by hand would be cumbersome, and the result depends on whether or not we are using signed or unsigned integer values. In any event, the decimal equivalent is not simply the decimal equivalent of each nibble concatenated together. CD, CFD6EC6 DC is not equivalent to 1251136 and so forth. Using a calculator to perform the conversion to an unsigned integer, we find that this is equivalent to this decimal, this number. Every two hexadecimal digits align neatly on byte boundaries. This makes the memory layout of hexadecimal data visually obvious. However, when viewed this way, the Indianness of the system must be considered. On the x86 architecture, multi-byte values are stored in memory in the little endian format, which means that less significant bytes are stored at lower addresses. So this value would appear in memory when listed by byte address, like this and that. Hexadecimal notation also helps highlight certain prominent bit patterns. So we've got 0, all bits are clear, and then we've got F, all bits set, and we've got even low bit set, which is it's how this is how it is written. And when it's odd, this is how it's written at the end. We've got a 1, And when it's a higher bit here, it's like that. And when it's a high bit set, it's like that. The last two patterns, 0xxx and 1xxx, are useful when examining unsigned integer data because the highest bits the highest bit in the most significant byte is used as a sign bit and determines whether or not value will be regarded as a negative number. So now we'll be moving on to we'll be doing our the octal notation is a base 8 positional notation. Valid digits are 0, 1, 2, 3, 4, 5, and 6 and 7. Note particularly that the symbol 8 is not an octal digit. This notation was much more common before 8 bits became the de facto standard size of a byte. The interesting characteristic of the octal notation is that any combination of 3 bits required at most one octal octal digit. Following the same method used above, we can determine that the highest unsigned value that n octal digits can represent is an a to the power n minus 1. The numeric notation syntax. The lexical convention for specifying different numerical notation differs from one programming language to another. Some languages support more than one convention. Some languages do not support certain notations at all. This table demonstrates the representation of the ASC character code for a blank space in a number of different languages. I've done a slide on ask, which is the SC double I. Um, let's go through that. So an ask is an acronym for the American Standard Code for Information Interchange. It is the code for representing a 128 English characters as numbers, with each letter assigned as a number from 0 to 127. So for example, we've got an ask, that's how it is pronounced. Ask code for uppercase M is 77. Most computers use ask codes to represent test text, which makes it possible to transfer data from one computer to another. So what they mean here to say, most computers use this code to represent test test text text text, my people. It is a text. So this is what they mean. Oh, sorry. This is what they mean in terms of different code. It's a S code to represent text. So most depending on which language they use this kind of format and so forth. So going back to our learner guide, this table could demonstrate the representation of the ask character code for a blank space in a number of different languages. So in ANSI, in hexadecimal, we've got a 0x20, in decimal is 32, in octal is 041, and in binary we don't have one. Free basic, we've got the sign and an H and a 20 and a 32 and an end. We normally use this as an end abbreviation end. That's how we normally, yes, this you basically, but now it's an end H2032 and HO 240, and in binary it's this. So this is what you can go through on your own just to see what this as character code is used for. We've got displaying values in different notations. We've got different logical data types. We've got the numeric data type. We've went through that. Numeric data types simply means numbers. Numbers come in a variety of different types. We've got integers. An integer is a whole number. It has no decimal or fractional parts. Integers can be either positive or negative. Examples are that 12 for 45, 1274, so forth, minus 3 is an integer. We've got the real numbers. Any numbers that you could place on a number line is the real number. Real numbers include whole numbers, integers, and numbers with decimal fraction parts. Real numbers can be positive or negative. So we've got 1, 1.43, 4534, and so forth. We've got currency. Currency refers to real numbers that are formatted in a specific way. Usually, currency is shown with the currency symbol and usually two decimal places. We've got, as you could see, it's euros. It's 12 euros 45 cents, and we've got no, it's pounds. Is it euros? Yeah, it's euros. It's euro. It's 12.45 euros, and you've got pounds. It's 999.00 pounds, and we've got dollars. So yes, these are your currencies. And we've got percentages. Percentage refers to fractional real numbers that are formatted in a specific way out of 10 with a percent symbol. So the real value of 0.5 would be shown as 50%, and the value of 0.0 would be shown as 1% and rounded off to 1%. So and the number 1 point would be shown as 1.25. Examples: 100%, 25%, 120, 1200%, and minus 5%. And then inside the computer, the 50 is stored as a real number 0.5, but when it is displayed, it is shown formatted as a percentage. Alphanumeric data text. Alphanumeric, often simply called text data, refers to data made up of letters, alphabet, and numbers, usually symbols. We are familiarized with these symbols, and spaces are also allowed. Let me just check whether I can show you these kind of symbols. These symbols, we've got plenty of symbols. Show more symbols, please. Yeah, these are kind of symbols that we are talking about. We've got numerous kind of symbols that we have, so there are so plenty. Yeah, you could just go through them on your own and just familiarize yourself with them. So going back to our slide, examples are dog, a little mouse, ABC, and etc. And text data is often input to a computer with speech marks around it. Monkey. These tell the computer that this is a text data and not a special command. We've got data and time. We've got date and time data. Date and time data are usually formatted in a specific way. The format depends upon the setup of the computer, the software in use, and the user preference. Date examples is often like this. And examples is 11 a.m. and so forth. With inputting dates, particular care has to be taken if the data contains American style dates and the computer is set up to expect international style dates, or vice versa. The date this date 060908 refers to 6th September 2008 in the international system, but would be 9th June 2008 in America. Check your computer settings. We've got the Boolean and logical data. Is sometimes called the logical data, or in some software a yes or no data. Boolean data can only have two values, true or false. So examples is true or false, on and off. Similar like your binary. When it's one, it's on. When it's zero, it's off. So when it's true, it has to be one. When it's false, it has to be zero. Yes or no. It's something similar to that. Note that the true and false can also be shown as yes, no, and on and off, or even graphically as a tick boxes or tick or unticked. Selecting data types: when we are presented with data to be input into a computer system, we must analyze it and select appropriate data types for each value. E.g., the following data we might use the data types shown: date, name, height, date of birth, phone, pay, rate, tax rate, and so forth. Date type is text, real date, alphanumeric, currency, and percentage. So we've got different internal representation of data types. IDL data types, we've got digits, bits, bytes, and words. We have gotten to the place where you would need to know a little about the internal workings of a computer, specifically how a computer stores numbers and characters. Humans think of numbers expressed in powers of 10 or decimal numbers. This means that there are 10 digits from 0 to 9, and you begin counting with these digits. When you reach the highest number expressible by a single digit, you use two digits and generate the next series of numbers 10 to 99, and so on with more digits. This can be expressed mathematically. Note the following when we use 5199 as an example. Fundamentally, all computer information is stored in the form of binary numbers, meaning powers of 2. How many digits? 2. There are 0 and 1. The highest number expressible by a single digit is 1. The two-digit numbers range from 10 to 11, and so on with more digits. But what decimal numbers do these binary numbers represent? Let's look at an example using 1101. Notice that we use the base of 2 instead of base of 10. 00112 to the power 3 is 3 plus. This basically is what we have done on the previous slide that I've shown you. It's more similar to this one. I'll make sure that this will be some of the documents that I will send you through to our e-portal. So let's continue further into our learner guide. The binary number 01101 is a 4-bit number. What decimal numbers does the binary number thus equal? For convenience, computers and their programmers group the bits into groups of 8. Each group of bytes is called, if each group of 8 bits is called a byte. So let's go back here. So from 1 to 8, it's 1 byte. From 1 to 8, it's 1 byte. So that's how they mean when they say they group each byte. So from each group of 8 bits is called a byte. Consider then the binary number 111111 is the maximized size number that can be stored in a byte. Okay, let's look. This it's you can go through it on your own and just read further and understand as what it's nothing. You just have to read and just gain extra knowledge in terms of and understand further. You can read that on your own. Let's go to integer data types. Integer data types store the numbers just like you would expect. IDL supports integers of 4-digit length, 1, 2, 4, and 8. The shorter the word, the less memory required. The longer the word, the larger the numbers can be. Different requirements require different compromises. one byte, the byte the byte data type, that the byte data type is a single byte long and always positive. Therefore its values run from 0 to 255. Images are always represented in bytes. The data might not be in bytes, but the numbers that the computer sends to the video processor card are always bytes. Video screens require lots of memory and really quick processing speed, so bytes are ideal. You generate an array using a byte a byte r a byte r for sized array, or bind gen for index array. You can generate a single byte variable by saying x equals to 3b, for example. If a byte number exceeds 255 during a calculation, then it will wrap around, for example, 256 wraps to 02257 for etc. 221, etc. A 2 byte integers and assigned integers. With 2 bytes, numbers that are always positive are called assigned integers. They can range from 0 to 256, 2 to the power minus 1, or 0 to 65,535. You generate an array using an untar for zeroed array, or untigen for index array. How do you think assigned wrap around? Normally you want the possibility of negative numbers, and you use integers. The total number of positive integer values is 256, 2 to the power divided by 2 is equals to 32,760 768. One possible value is, of course, 0. So uh, so the so the number of integer and positive values differ by 1. The choice is to favor negative numbers, so integers cover the range 32,768 to 32,768. You generate an array using an inter or an in-gen. What happens with the wrap around? But if x is equals to 5 and x is equals to 30,000 and z and y and so forth. You can check it out. If you don't understand, guys, feel free to send emails. We'll go through this together. It will be good for us to go through this together instead of explain. I just want to see your participation in terms of these videos. So I would want a feedback as much as possible. And so if you don't understand anything, feel free for you to come through, and I'll explain better. So the rest of these guys, I'll leave it up to you to read out for yourself and understand where you are puzzled. Send me an email or a WhatsApp. I'll see to it that I will explain this much more better. We've got floating data types in ADL. The problem with integer data types is that you can't represent anything other than integral numbers. Okay, to get around this, the floating data type uses some of the bits to store an exponent, which may be positive or negative. You throw away some of the precision of integer representation in favor of being able to represent a much wider range of numbers. 4 bytes floating point means 4 floating decimal point. It can wash all around with floats. The exponent can range from about minus 38 to minus greater than or equal to plus 38, and there is about 6 digits in precision. Let's look at the 8 bytes double precision like float, but the exponent can range from about 307 greater or less than plus or minus 307 to 307. There is about 16 digits of precision. Let's look at the strings. We store characters, letters, symbols, and numbers. A string, a constant such as hello, consists of 5 letters. It takes 5 bytes to store this constant. 1 byte for each character. There are 265 possible characters for each of the bytes. Let's look at structures. You read further on the strings. I will just summarize in terms of the topics. The structure are special data types that allows variables of different types and sizes to be packaged into one entity. This is different from an array where every element must be the same data type. Let's look at the different logical operators. We've got and, or, and not. Logical operators are typically used with Boolean logical values they are return a Boolean value. However, the and this operator, this one, actually return the value of one of the specified operands. So if these operators are used with non-Boolean values, they may return a non-Boolean value. We've got logical operators. Common Lisp provides 3 operators on Boolean values and, or, and not. Of these and or are also control structures because their arguments are evaluated conditionally. The function not necessarily examine its single argument, and so is a simple function. This table is the logical operators are described in the following table. So you'll read through this. Fortran has 5 logical operators that can only be used with expression whose results are logical values, true or false, and all logical operators have priorities lower than arithmetic and relational operators. Therefore, if an expression involves arithmetic, relational, and logical operators, the arithmetic operators are evaluated first, followed by the rational operators, followed by the logical operators. These 5 logical operators are not, which is logical not, and logical and, or logical or, which is equivalence, and NQV, which is not in the equivalent. So guys, before we could go through to our session 3, I would like you to uh, send me feedback in terms of our second session, in terms of where you couldn't understand. I require everyone to send me feedback as to where you couldn't understand, and you want to discuss further some of the things that you've encountered, you faced, like your bytes, your difficult numeric data types. So I would like you to contact me. Let's engage and prepare for our next session, which is session 3. So guys, I hope you are well where you are. Yeah, you are safe and you're studying. Let's go through our learner guide and study, because of in due course we'll be sending our formative and the summative. So guys, let's prepare ourselves and do what is required. So until we proceed to our next session, stay safe and take care.